Let's build an adder for two binary digits, or bits. We'll start with the truth table. Since there are two inputs, one for each bit, and each bit can only take on two values, that gives us a total of four possible combinations of input values. If both inputs are 0, their sum, 0 plus 0, is 0 in the output. Also, if one input is 1 and the other input is 0, then we get the sum 0 plus 1 equal to 1 in the output. But we have a problem if both inputs are 1, since 1 plus 1 is 2, which is too large to store in one bit. Recall, the binary representation for the number 2 is 1, 0. In this case, we actually need to include one extra output called carry out to our bit adder to capture that extra digit. The first digit would be 0 in this case, and the carry out would have the value of 1. How do we build this device using logic gates? We look at the truth table. Notice that the sum output column compared to the inputs is exactly an XOR gate. Next, if we compare the carry out column to the inputs, it is just an AND gate. Thus, two logic gates, each connected to the inputs, can be used to create our adder. This simple bit adder with carry out is called a half adder. Why is it called a half adder? Even though we've accounted for an overflow from our sum using a carry out output, notice that we haven't included a way to carry in an overflow from another adder into this one. This is a necessary capability for more complex calculation circuitry. We won't go into the full analysis here, but here's what a full adder circuit looks like and its associated truth table. Instead of two inputs, the carry in is used as a third input, and its value is summed up with the other inputs. For example, the last row in the truth table shows the inputs as 1, 1, and 1. When summed, they equal 3. Notice that the output value is 1 and the carry out is 1, which gives us the number 1, 1 in binary, which is the representation of 3 in decimal.